Welcome to Hot Chips 2024. Poster Lightning Talks.
All right, welcome to the slightly delayed lightning talks. These are each of the students has 2 minutes to present their poster. If you have any questions about it, which you should, then you can go talk to them afterwards. So our first presenter will be Vyansa Schmolbach from the University of California at Berkeley.
Hi, I'm Vyansa Schmolbach from the University of California, Berkeley, and I'll be presenting not one, but two class chips, Nectar and Rasok. Specialized chip design needs to be agile in response to rapidly evolving domain-specific requirements, such as robotics and machine learning. As a demonstration of agile chip methodology, we present two heterogeneous system-on-chips designed by mostly undergraduate students with no prior chip design experience. In just 15 weeks, students go from making high-level design decisions to sending a fully DRC-clean GDS to Intel Foundry services for fabrication in the Intel 16-nanometer technology. To accomplish this, students utilize the open-source Chipyard framework, which includes existing core IP as well as support for creating custom accelerators, which are either tightly CPU-coupled or memory-mapped I/O operated. Chipyard also contains the Constellation framework, which was used to generate unidirectional knocks for each chip. Both 2mm by 2mm chips operate at 400 megahertz at the nominal supply of 850 megavolts. Our first chip is Nectar, a near-cache transformer accelerator chip. Nectar accelerates ML workloads with a set of near-memory compute engines, CPU-coupled sparse matrix accelerators, and best offset prefetchers. We demonstrate Nectar by running a tiny llama inference model with the prompt of telling bedtime stories. Our second chip is Rasok, a robotics application system on chip. Rasok accelerates robotics applications with Kalman filter and LQR accelerators. Additionally, Rasok implements a memory tagging extension on an out-of-order core and a switch capacitor voltage regulator. We demonstrate Rasok with an inverted pendulum balancing application. Both chips are capable of booting Linux and connect to DDR4 backing memory, and you can see both of them working with the demos I explained at our demo session. If you'd like to hear more, please come to our posters and check out our demos. Thank you.
Thank you, Vyansa. That was pretty good. We had just 15 seconds to spare there. So Picasso, next presentation is Picasso from Sungyeob of KAIST.
Good morning, everyone. I'm from KAIST. I'm excited to introduce Picasso, an area and energy efficient end-to-end diffusion model designed to address the key challenges faced in diffusion models. Accelerating diffusion model requires carefully balancing accuracy and bit precision in low bit quantization and effectively addressing latency in non-matrix operations. Picasso is our solution to these challenges. Built on a 28-nanometer process, Picasso is designed to optimize diffusion model workload by focusing on three key features. First, hyper-precision data type. This novel data type allows for high-resolution commutations without compromising accuracy, even at low bit precision. Second, hyper-efficient reconfigurable array. Optimized for matrix operations, HERA enhances processing efficiency, ensuring that Picasso can handle demanding computational tasks with ease. Last, unified non-matrix processing engine. Addressing the latency issues associated with non-matrix operation, UMPE ensures smooth and efficient processing across various tasks. The results speak for themselves. Picasso delivers up to 26.8 times better performance, 30.5 times better area efficiency compared to previous accelerators. If you are interested in learning more about how Picasso can revolutionize your diffusion model workload, I encourage you to visit our post session. Thank you for your attention.
Thank you, Sungyeob. Our next speaker is Gwangtae Park, who's also from KAIST, and he's going to tell us about SpaceMate.
Good morning, everyone. My name is Gwangtae Park from KAIST, and today I'd like to introduce the brief summary of my work nicknamed SpaceMate. So it tries to accelerate the NeRF SLAM, which is a fully AI-based SLAM algorithm. So its main advantage compared to traditional SLAM algorithm is that it can predict the unseen area that has not been captured by the cameras in the agent. So, however, it is very hard to accelerate in the current commercial devices compared to the traditional ones. So I tried to do some hardware and software co-optimization to resolve such NeRF SLAM's computation bottleneck. In the software perspective, a batch-level conditional computing by replacing the conventional neural network into the sparse mixture of experts is proposed. So it reduces the number of max without sacrificing the accuracy. On the other side, in the hardware perspective, to solve the dynamic behavior of the sparse mixture of experts, an out-of-order data flow is proposed to handle the irregular batch access. As a result, we achieved the state-of-the-art performance, and it was demonstrated on the open-source robot platform. So my poster is at the wall side, so if you are interested, please come and visit me. Thank you.
Thank you, Gwangtae. Our next speaker is Kai-Do Nguyen from the University of Tokyo, risk-based system of chips for IoT.
Good morning, everyone. My name is Yui. I'm from the University of Electrocommunication in Tokyo, Japan. So in this work, I show in here is I make the system on chip that we try to minimize the power consumption to the idea that we can operate them without the battery. So we make the two different variants of the serial RISC-V processor, and then we build the system on chip around it. So we measure in terms of area performance and power. So and we also fabricate these two SoC on SOTB65, which is the low power technology that allows us to do the biasing on chip. So we got some measurement result. So if you feel interested, you can come by the poster. Thank you very much.
Thanks very much. Our next speaker is also from Tokyo, so Q will tell us about a trusted execution environment for RISC-V system on chip.
Hello, good morning, everyone. So my name is Gil from University of Electrocommunication in Tokyo, Japan. So I bring here today our work on the trusted execution environment RISC-V system on chip. So RISC-V has dominated the chip domain in the field next year. So the problem when they become common is that the data need to be protected over the threat from the hacker. Another thing is that the openness of the RISC-V allow to integrate multiple third-party IP into the RISC-V system. So our solution is that we isolate the sensitive data in the RISC-V system from the rich environment where something like the application, the OS runs. So we propose a framework including an isolated subsystem based on the multi-site system on chip and the hardware accelerator for the crypto. So our works achieve the best balance between the flexibility and the security. So if you would like to discuss more about this topic, please come to our poster. Thank you.
Thank you very much. Good. All right, our next speaker is from the National University of Singapore, Animesh Gupta, and he will tell us about Cognivision.
Good morning, everyone. I am Animesh Gupta, a PhD student from National University of Singapore. Today, I invite you all to my poster Cognivision, which is a milliwatt power SoC for always-on smart vision systems. So Cognivision presents an end-to-end hierarchical execution from a CMOS imager to AI and communications, which allows us early gating of readout and compute for true system power reduction. It is a cognitive system at very low DNN activity, which means traditionally power-hungry DNN accelerator is pushed to minor power contribution of the overall system. Also, it is software programmable through a RISC-V, and it has an on-chip wake-up receiver. On this slide, I show a die micrograph in 40 nanometer, which is fabricated through TSMC and occupies a total area of 36 millimeters square. For more detailed discussion, I invite you to my poster. Thank you.
Thanks, Animesh. So our next presenter will be Sungyeob Kim from KAIST, who's going to tell us about a large low-power LLM processor.
Hello, I'm Sungyeob Kim from KAIST, and I propose the neural computing-based large language model processor with the Big Little network and the implicit weight generation for on-device AI. These days, the neural computing method is widely used for low-power AI applications. It mimics the human brain operation. When each neuron receives the input spike, it accumulates the weight to increase the membrane potential. And when the membrane potential exceeds the threshold, then the output spike is generated and transferred to the next neuron. So this operation is called by the integrate and firing operation, and it is repeated at every cycle until the user-specific time window. So during this operation, the number of accumulation and energy consumption are proportional to the input spike, and the number of input spike is proportional to the amount of information. So when there is a lot of information, the neural network consumes large energy. When there is few information, the neural network consumes low energy. But in contrast, the conventional deep neural network always requires the fixed number of multiplication between input and weight, so it shows the mild power variation depending on the amount of information compared to the neural network. So there is the energy trade-off between two different network types, so we combine these two models to achieve optimized energy consumption. When there is few information, the neural network is used for inference, and when there is a lot of information, the conventional deep neural network is used for inference. And the figure on the right shows the measurement system of our proposed chip. It can support the language modeling, translation, and summarization. And also, it can achieve only 18.1 microjoule per token for language modeling with GPT-2. Thanks for listening.
Thanks very much. Our next speaker is Larry Tang from CMU. Oh, there we go. Look at that. It works. Stop that. Today's lesson is try not to have multiple timers going simultaneously because terrible things happen. All right, I give up. Okay, so after that brief interlude brought to you by iOS ineptitude on my part, we have Larry Tang who's going to tell us about his FFT hardware.
Good morning, everyone. I'm Larry Tang from Carnegie Mellon University, and today I'll be talking about our work towards an automated FFT accelerator design methodology. So in this work, the problem we're trying to address is that current FFT hardware accelerators are usually designed as standalone blocks or IP blocks, and then this leads to relatively fixed functionality and makes it challenging to integrate into systems and optimize with application software. So in our approach, we propose to hardware accelerate only a software FFTW codelet, which essentially computes a small radix butterfly to enable a large amount of flexibility in the software. And eventually we would like full software stack integration and hardware generation using the spiral code generation system. So as a first look towards this, we've fabricated a test chip consisting of a radix 8 twiddle codelet accelerator in a TSMC 28nm process, where the radix 8 butterfly was automatically generated using spiral. And ultimately, we would like a full end-to-end system in which both software and hardware are automatically generated. So please feel free to stop by the poster for any discussion or Q&A.
Thank you, Larry. Our next speaker is, wait a second, that doesn't, we got the right one? We're looking for the PACE person back there. Oh, we are not going to have this talk, so if you want this poster, then I guess you will have to go look for it. The next speaker is actually here, is Joo-Young from KAIST, and he's going to tell us about his neural network-based 3D perception SLAM.
I'm Joo-Young from University in South Korea. It is a great honor to be here and opportunity to have opportunity writing my talk. I will introduce the first LSPU, the first cementing LiDAR SLAM system on chip for autonomous driving system. Cementing LiDAR SLAM is essential component for advanced autonomous driving system, providing 3D information, including 3D perception, localization, and mapping. However, there was no chip implementation for real-time cementing LiDAR SLAM. Our chip is the first cementing LiDAR SLAM processor integrating point neural network-based 3D perception into SLAM pipeline with 5 types of heterogeneous architecture to fully support each algorithm. It is fastest processor with lowest power consumption. So please stop by my poster and enjoy the details of the LSP architecture. Thank you for listening.
Thank you very much. Our next speaker is Junha Ryu, who will tell us about his graphics processing unit.
Good morning. I'm Junha Ryu from KAIST. And today I'm going to talk about a neurographics processing unit for fast 3D modeling. Recently, reality capture into the 3D space becomes emerging with the rise of the metaverse. And we focused on the 3D modeling using AI-based 3D modeling technique called the neural radiance field. So here's the 3D modeling process using neural radiance field. And given input to the images, NeRF trained the DNN model to evaluate the color and density of the samples. And after completing the modeling, users can obtain the rendered images from any viewpoint as shown in this figure. And implementing the neural radiance field on mobile devices have 3 hardware challenges, and we optimize with the software hardware co-design. First, we convert the non-streaming off-chip memory access to streaming off-chip memory access. And second, we achieve the low power interpolation by designing the heterogeneous interpolation unit. And third, we adopt the coarse grain skipping method for efficient MLP acceleration. And we implement the chip with the Samsung 28nm technology, and we achieved 20 times faster modeling speed compared to the Jetson TX2. And we also implement the demonstration system integrating our chip package to show the real-world 3D modeling scenario. And if you're interested in the detailed information, please visit our poster. Thank you.
Thanks very much. Our next speaker is Chen Lu from National Chuncheon University in Taiwan, and we're going to talk about an intelligent audio processing engine. So,
Good morning, everyone. I'm Zhentong Liu from National Zhongzhen University, Taiwan. And we proposed the 14 nanometer 13.88 TOPS per watt FCDNN engine for 16-bit intelligent audio processing featuring weight sharing and approximate computing. A real-time disassoric voice conversion is the application example in this work. Here are two audio samples in Chinese from a speaker with disassoric one before conversion. Okay, it is not work. And the other is after conversion. So you can invite our poster, you can hear this voice sample in our poster. And this sentence means the electricity bill seems to have increased recently. And if you come to here, you will notice the converted voice is much more clear and easier to understand in Chinese. We've developed weight sharing and approximate computing for this AI engine using digital in-memory computing in 14 nanometer. This work achieves a 17 times improvement in energy efficiency compared to the previous work. We invite you to visit our poster for more details. Thank you.
Thank you. I can vouch for the fact that the audio does sound much clearer in the revised version. I can't vouch for what he says, but it does sound clearer. So go see the poster. Our last presentation is a smart cache for a smart NIC from Anas from Purdue, and away we go.
Hi everyone, my name is Anas Zulfikar, and I'm presenting a smart cache for a smart NIC. Now, the end host network is the cornerstone of your data center network, and within the end host, the virtual switch plays a key role because it allows you to virtualize your entire data center network topology that you present to your virtual endpoints, your VMs, and your containers. Now, because performance is key here, for performance optimization, these virtual switches are divided between a slow path and a fast path. The slow path, as you can see, is in figure 1 at the top. It basically implements an intricate pipeline of packet processing tables that you traverse when an incoming packet misses the fast path. When the processing is complete, you compose all of these matched rules that you found into a single cache entry and install into the fast path so that subsequent packets can get very fast lookups compared to the slow path. A lot of SmartNIC products, in fact, all that I know about now allow you to offload this fast path cache down into hardware. And performance is very important because if you miss the fast path cache, then you will go from nanosecond level latency to anywhere between microseconds and milliseconds, depending on which CPUs, either on the SmartNIC or the hosts, are processing your slow path traffic. Now, two important assumptions have guided the designs of these fast paths until now. One assumption was that multi-table lookups are expensive, and therefore this has necessitated the use of single table caches in the fast path. And you can see that this is clearly a software optimization. These caches were not meant to be used on hardware. The second assumption was that the hardware on, basically, the second assumption has been that the only locality information that is available for you for generating these cache entries has to be extracted from the traffic. So you're only looking at the temporal locality. But we have shown with our work that both these assumptions now need to be revisited because one, on SmartNICs, hardware is capable enough that you can create a pipeline, a small pipeline of a sequential pipeline of small number of tables, lookup tables. So you can partition your cache across a sequential pipeline. And the second assumption of only having temporal locality is we've also challenged that because the slow path pipelines are programmable. So now you can, instead of composing the whole traversal and installing a single cache entry, you can unroll this whole traversal, find optimal partition points, and install sub-traversals. And this allows you to share sub-traversal level compute across your flows. And because you have multiple tables, if you install these cache entries correctly, you are able to capture a cross product of rule space more within these sequential pipelines compared to a single table while using the same cache budget. And we have shown with our results that if you have a 32,000 cache, if you partition it across 4 tables, 8,000 entries each, then you can get 3 orders of magnitude more rule space that you can capture in there, a 51% higher cache hit rate, and 90% reduction in the total number of misses. If you find this interesting, I'm presenting my poster outside. Yeah, feel free to approach me, and I'll be more than happy to share more details.
All right.